Hello, today we're going to be talking a little bit about some electric fields and electric potential to go along with our studies of electrostatics. So, a force field surrounds a electric charge. There is the electrostatic charge where like things repel and opposite things attract. So, around a singular charge, you can figure out what the force will be, how big the force on a positive or negative charge will be around this one charge. So, say I've got a proton here with a positive charge, I can figure out how far away and how big the force will be on a charge no matter where it is. And that is the idea of this field around the charge, where the force acts different in all of these different spots, but I can figure out exactly what that force would be. This is my force field, the field of forces around a charge or group of charges. It's really similar to gravity and gravitational fields, where gravity can hold a satellite or the moon in orbit around a planet. The electrical force can hold an electron in orbit around a proton, or we can see how gravity or the electric force would change if this were to get bigger, or if the charge of the electron were to get bigger, or if they were to move closer. It's all imagining or determining the size of the force around an object. So when we are thinking about electric fields, we draw something called field lines, and I'll show you an example in just a second. But when we are drawing these field lines, it's a bunch of arrows. It's going to be a page that's got a couple of dots for your charges, or circles or squares or whatever for your charges, and then a whole bunch of arrows. And those arrows will always point away from positive charges and towards negative charges. So the arrows are going to be proportional to the charge, to how big, the size. And those arrows don't actually exist in real life. It's not, you can't put on a special pair of glasses to see those arrows around you. But electric fields do actually exist. These are real things where you can figure out how big a force is around an area. So here is what some field lines look like. If I have a positive charge, if this is a proton or if this is a positively charged ion, then I've got field lines that point away. So you can think of the electrons have left the atom to make it positively charged. So my field lines point away. For a negative charge, an electron or a negatively charged ion, where there are more electrons than protons, the field lines will point towards it, pointing in towards the field, towards the charge. So I can think about, what does this look like when I have multiple charges? If I've got a positive and a negative, the field lines will go from the positive into the negative. On all of these, and if I go back to look at the positive and the negative point charges, it goes out in all directions. The force field is in all directions around this object. So when I've got a field lines between both a positive and a negative charge, I have to think about what is going on all sides. And this is something that you can kind of see. It's not looking at arrows, but you can kind of see when you play with like charged magnetic fields. It is very similar to that. And you can imagine here we have a positive charge and a negative charge. And you can see that flow. You can see the shape as it goes out of one and into the other. If you have similar charges, those are going to repel. So in the middle, there's going to be things that are running into each other, but not wanting to run into each other. So you can see they curve away a little bit. Remember, like charges repel and opposite charges attract. We can identify the strength of this electric field by thinking about how big is the force at a given spot. So if I want to think about what is the force on a test charge, on a small, simple charge that I'm just going to put in this field to figure out what the force is, that can tell me E, which is the strength of the field, or what is the measurement of this electric field. So you could either use KQ over D squared, where K is that same electric constant from Coulomb's law, Q is your charge, and D is the distance. Or that is also equal to the electric force divided by the charge, Q. So let's look at this example here. I want to know the magnitude of an electric field on a positive test charge of 4 times 10 to the negative fifth coulombs. That will be my Q. The charge experiences a force of 6 newtons, so that is my force, F. I'm going to double check my units. I've got coulombs and newtons. Those are both good. I don't need to mess with anything. So I will plug 6 in for F and plug 4 times 10 to the negative fifth in for Q. And when I put that into my calculator, I get 150,000 is the value for the electric field. And the unit there is newtons per coulomb, or newtons over coulomb, or newton coulombs. So this would be 150,000 newtons per coulomb is the magnitude of this electric field. Here's another example. Now I don't know what the force is, but I know that I've got an electric field that is 3 nanometers away from a metal sphere with 8 electrons. So it seems like maybe I'm missing some information, but it's all there. You've got everything that you need. K is that electrostatic constant, 9 times 10 to the ninth. Q, we're going to get from these 8 electrons. And the charge of an electron is a constant value that is on your formula chart. The charge of an electron is 1.6 times 10 to the negative 19th. I'm sorry, negative 1.6 times 10 to the negative 19th coulomb. We've got 8 of those, so Q is 8 times the charge of an electron. And my distance here is given by 3 nanometers. We don't work in nanometers, we work in meters. So I need to convert that. And also on your formula chart, it has at the bottom, nano is 10 to the negative ninth. So this is the same as 3 times 10 to the negative ninth meters. If you plug all of those in, K, the constant, Q, 8 times the charge of an electron, and D, 3 times 10 to the negative ninth meters, you would get the force of the electric field. So you can do this with either of those 2 equations. They are the same thing, and they are both on your formula chart on the side here. A charged object, because it is in an electric field, has potential energy. It's a little bit different than the potential energy when you were sitting at the top of a roller coaster, but it's the same idea. It's got the potential to do work, or you have to do work in order to push it against the electric field. If I go back to thinking about the comparison to gravity, I am holding this pen up and I have given it potential energy because I have done work to lift it and work against the field. The gravitational field pulls everything towards Earth because Earth is so big. And so by lifting and going against that field, I had to do work. So pushing a charged particle against the electric field, you have to do work. And the change in potential, or the potential difference, is here given by the field E times the distance that you move something, or KQ over D. Again, K is that electric constant, Q is the charge, and D is the distance. And that will give you electric potential, the potential difference, or the voltage, V. All of those are referring to the same idea. So if I want to know the potential difference on a positive 5 millicoulomb charge that is 2.5 meters away, I plug in 2.5 as my distance. K is 9 times 10 to the ninth, and Q would be 5 millicoulombs, but we don't want millicoulombs, we want coulombs. So I will plug in 5 millicoulombs is the same as 5 times 10 to the negative 3 coulombs. So this one would be 5 times 10 to the negative 3. Here's another one where, again, I'm going to use different pieces of information or a different version of the same equation to figure out the voltage produced by a 100 newtons per coulomb electric field. That's E. If the particle is 3 centimeters away, that's D, but we don't work in centimeters, we work in meters, so I would plug in 0.03 as my distance. And that is electric fields and electric potential. Take a look at the different pieces of information that you have to figure out which version of the equation you need to use. Because remember, for each one, there are 2 different versions, and you can find voltage and electric fields. All of your teachers are here to help if you have any questions. And that's it. Bye-bye.